Okay, hello. Good morning, everyone. Welcome to Data 100, lecture number 6. Today we're going to be talking about some more data visualization. And today will be the first lecture where I don't write any code on the screen for you. Instead, we're going to be talking about the concepts and principles that go into making a good data visualization. As you know, Project 1 is due tonight, so please make sure you have that turned in. Again, we have small group tutoring starting this week, and every week from now on, we will have tutoring available for you. So we're going to send out a form every week. We're going to update the times, I believe, on a weekly basis. So do keep an eye out for that form. It's especially handy if you're having trouble with some of the conceptual material from the class. Okay, homework 2 will be out tomorrow, and homework 3 will be out Friday. Yesterday, I accidentally put on my slides that homework 3 was due 1 week from today on Tuesday. But it's actually due the following Friday because it's long. So I suggest you get started on homework 3 early. Okay. I do want to quickly run through the procedure for submitting assignments one more time because it's been updated slightly since the last time I demoed this to you. So when you submit Project 1, please make sure you follow these steps. Okay, so you go on Data 100 and you go to the course website. Click on Project 1, start that guy up, and what you should make sure to do is run that last cell of your notebook. You really want to verify that on OKPy, the notebook that appears is the same as the notebook that you expect to see. So usually what this means is, I'm going to open this. Hello. Okay, so I'm going to run the first cell. I'm going to scroll all the way down here because I didn't do the project. I was a bad student. But if I want to submit this project anyway, I'll run this cell. Okay, it's going to say generating PDF. It's going to say, so this appears if you haven't logged into OKPy in a while. So I'm going to write down my email, press enter, click this link, confirm. Hello, I'd like to confirm. Okay, paste that code back in here, press enter again, and then you should see this URL at the very bottom. You should see submission successful for your email address, and you should be able to see this link. You should click this link, okay, and make sure, you should scroll all the way to the bottom and like make sure that your last changes are reflected in this notebook, because this submission is what we're going to see when we run the autograder. Sometimes what happens is you run that cell, but your notebook hasn't saved yet, which means that you submit an older version of your notebook, and that will cause you to lose points if you haven't finished the problem yet. Okay, so do make sure, you really want to like make sure you give yourself as many chances to get full credit as possible. Okay, and one way to do that is to make sure like you scroll through this notebook on OKPy and like look through and make sure that everything is good to go. Okay, so this is part 1 of submission. There is a second part where you have to submit the PDF. All right, so what you should do is take off this notebook, link from the URL here, and get to the folder where your Project 1 notebook lives. And if you ran that last cell successfully, you'll also see a proj1.pdf file. You should download this file, and then go to Gradescope. Okay, yes, I'm logged in as a student on one of my other Gradescope accounts. I'm going to click here. I didn't submit Project 1 yet, so you're going to click this, submit the PDF. Okay, so I'm going to select project1.pdf, submit that. And you have to go through your PDF and assign pages to questions. Okay, so you're going to see here some images corresponding to your PDF. And what you have to do is label the pages of your PDF according to the question that they correspond to on the assignment. So if you can't see these images, you can zoom in with this little bar here. So I'm going to zoom in, and I'm going to say, this looks like question 1E, these 2 pages. So I'm going to click these 2 pages and then 1E. Okay, so now these pages are labeled for the question. If you don't label your pages, your graders will not see, like graders will think that your work for a different question was, you're going to mix up the work for questions, and they're going to mark you off because they won't be able to see the work that you did. Okay, so you really want to make sure you have those questions marked in. Now, I know that last time for homework 1, we had some issues with the PDF conversion. Okay, so if the PDF conversion is for some reason breaking for you when you submit for project 1, what you can do is scroll down to the bottom here, comment out the last line of code. So I'm going to comment this out. I guess I can't change it. Okay, I can't comment it out. Okay, but what I can do instead is make a new cell, paste in the OK.submit because this cell usually works OK. Okay, so I'm going to paste that in. If the PDF generation doesn't work, an alternative or a backup plan for you is to Command P or go to like File, Print. And you can print, but you can say destination, save as PDF. And there are ways of doing this in I believe, every major browser. So whatever browser you want to do, you can save it as a PDF. And now you have a PDF for project 1. You still have to upload this to Gradescope. You still have to label your pages. But at least that way, if the JSign PDF thing breaks and you're getting close to a deadline, you can still print this out as a PDF and submit it and get your assignment in. OK, so make sure you run the last cell. If the last cell doesn't work, print preview, and do make sure that that PDF gets into Gradescope and that you have like both parts of your homework submitted. OK, any questions on this? All right. So today we're going to be talking about 6 broad categories, or 6 categories of principles for visualization. And instead of just listing them all to you one by one, I'm going to have you talk with your neighbors a little bit about 3 case studies, 3 example visualizations that need improvement. OK, so in 2015, there is a big controversy around Planned Parenthood, which is a government program. And they were accused of like selling fetal tissue to make profit off of it. I believe those investigations like didn't pan out. But one result of those investigations is that a lot of people in the government decided to like really take a hard, close look at this government program to try to figure out what was going on. Okay, so in 2015, Congressman Chaffetz showed this following plot. Okay, so I'm going to make that bigger for you guys. And one question I have for you, right here we have Planned Parenthood provides a bunch of services for their patients. Okay, and one service is screening for cancer, and another service is to perform an abortion. Okay, so we have these 2 procedures that are performed by the same organization, which has offices, I believe, still across the US. And so my question for you is, how many data points are in this plot? What is suspicious about this plot? And what message is this plot trying to convey? Why don't we start off by, why don't we do a warm-up, turn to your neighbor and try to answer these few questions. Go ahead. So how many data points are plotted on this chart? How many guys think more than 2? Everyone should be raising your hands. I hope there's more than 2. Okay. How many guys think more than 3? More than 4? More than 5? How many guys think this is a trick question? Okay, so it's a little hard to tell, but I do believe here that we have 4 data points. We have like the 2 million cancer screenings up top, and then we have like the 900,000 cancer screenings on the bottom here. We have the 200,000 abortions on the left-hand side, and the 300,000 abortions on the right-hand side. Okay, so it's kind of suspicious just at a first glance, because you have like you have like the labels for the heights, but then you don't have a y-axis for this plot. Okay, so what message do you think this plot is trying to convey? Yes, Julie?
It's trying to convey that there's some direct correlation between like the increasing of abortion and the increase of cancer screening.
Okay, so Julie says.
Some, like, causation.
Okay, so Julie says there's some correlation between when cancer screenings go down, the number of abortions go up.
Well, it's trying to convey that.
Yeah, okay, so it's trying to convey that message. Any other possible messages here? I think there's one more that I'm looking for. Any guesses? Yes, name and question.
My name's Anna, and then like, I think it's convey like the only like solid convey message is that both the abortion and cancer screening is changing during the like from 2006 to 2013. But the question is like, although the abortion is like the direction is going up and the number is going up, but like the cancer screening, the direction is going down, but the number on the two sides is it's still like the message is larger.
Yeah, so Ariana, is that right?
Yeah.
Ariana says the only thing she can conclude from this plot is that the number of abortions and cancer screenings are changing over time. You point out, rightly so, that on the right-hand side of this plot, we have 900,000 cancer screenings, but that's placed below the 300,000 abortions on the y-axis. Right, so all of these things are kind of suspicious. I would say, it turns out that for this particular hearing, I believe that they're trying to say that Planned Parenthood, in recent years, Planned Parenthood pretty much only does abortions and doesn't do some of the other useful things like cancer screenings, therefore implying that maybe we should cut the program because there are alternative like facilities for abortions. Something along those lines. I don't know the exact wording or the exact proposal behind this Congress report, but I have linked to it in case you're curious. Okay, so case number 2, if you go on the Bureau of Labor Statistics for the US government, they have surveys on labor. And here I have a plot that I've taken using the data from BLS.gov of the median weekly earnings for males and females by the education level. Okay, so I'm going to make that bigger. My question to you now is what comparisons are made easily and what comparisons are most interesting, and is this plot making the most or facilitating the most interesting or important comparisons? Go ahead and talk with your neighbor for a couple minutes. Go. All right, so let's bring it back together. So let's answer the first question. What comparisons are most easily made? What did you guys think? Any volunteers? Yeah, in the back. Andre, is that right? Hi, Andre. Yeah, so the more money you make, the money you make is correlated with your education level. So if you're more educated, you'll on average make more on a weekly basis, okay? Okay, what about interesting or important comparisons? So I would say yes, that is probably the easiest one to see. You see like this upward trend in the bars. Which comparisons are most interesting or important? Yeah, Julie?
That there's a huge gender disparity among income and that real kind of like degree health.
Yeah, so Julie points out that there's a difference between male and female weekly earnings at every single education level. So you can see here that the bar for males who have a high school degree is higher than the bar for females that have a high school degree, but that takes a little bit of time to see, so it's not immediately apparent. All right, one more case for you guys. Every April, there's a 10-mile run in Washington, D.C. called the Cherry Blossom Run, and they have the results available for like the past 10, 11 years or so. And in 2019, there turns out there were about like 17,000 runners. So there are a lot of people running this cherry blossom thing in Washington, D.C. I've never gone, but hope to make it out there someday. And what I've done here is made a scatter plot of the run time in minutes against the age of the runner in years. All right, so there's 70,000 points in this plot. And my question is, what's the relationship between run time and age? Okay, I won't ask you to discuss, but it does not seem readily apparent. You might conclude like a slight upward trend, but there are so many points plotted on top of each other that it's pretty hard to make a conclusion here. Okay, so now let's talk about some principles for visualization that can address some of the problems that we noticed in these past three plots. The first one I want to talk to you about is the principle of scale, all right? So in the principle of scale essentially says, make sure that the scales of your plot are consistent and useful for understanding. So what I've done is I've taken the data on the left-hand plot and replotted it in Python on the right-hand side, and I've actually put the same two lines on the same y-axis. And you can see here that the number of cancer screenings, the drop in cancer screenings, like just kind of dominates this plot. So you can see that the drop in cancer screenings is very high, and the corresponding or the relative change in abortions is not as high as the cancer screening. Okay, so this is the sort of pattern that you would see if you kept your y-axis consistent, rather than the one that you would see on the left-hand side. Okay. All right, so in general, like don't change your scale mid-axis. Don't use two different scales for the same axis. So you might see like plots where you have one y-axis scale on the left-hand side and one on the right-hand side. Those plots should be like generally suspicious in your eyes. Like sometimes they work out, but a lot of times they're used to try to like push forward some message that isn't quite there in the data. And in this plot, we see that it looks like the change in perception is that it looks like cancer screenings have changed a lot while abortions have not changed much at all. Okay. You might also consider the scale of data. Okay, so because in this plot, the number of cancer screenings is just so large, even if the change in abortions was quite dramatic, we wouldn't be able to tell because by plotting the two lines on the same y-axis, even if there was like even if the number of abortions jumped by like 2 or a factor of 3, it would be pretty hard to tell from this plot alone. And so sometimes what we want to do is take into account the scale of our data themselves. So what I've done here is plot the percentage change in number of procedures. Okay, so I've kind of normalized the difference by the percent change, and that way you can see that the number of cancer screenings fell by about 50%, while the number of abortions rose by about 15%, I would say, based on that bar there. Okay. Another use of scale is to reveal the data. So oftentimes you'll get data that have a heavy tail, like the one shown on the left here. So we have here one big spike at like 10, but then we have like two more really small spikes at 100 and 200 or so. And what we can do is choose the axis limits to fill the plot. So you don't have to show all the data within a single plot. Sometimes it's useful to zoom into a plot to reveal the pattern there. So you can see once I zoom in, there are like 2 smaller peaks at 5 and 7, and not necessarily just one big peak. Okay. If that bothers you, you can just keep in mind that you can use different plots to reveal different regions of the data. So I can make a separate plot for the little hump at 100, another plot for the hump at 200. But in general, like the point of choosing the scale is to reveal the pattern in the data, and that should always come first. All right, let's talk conditioning. So we talked before about how the labor statistic plot doesn't facilitate the most interesting comparison we want to make, which is a comparison between male and female salaries. We can change that by conditioning on the gender of the person, okay, or the gender of like this group. So we can see here by placing the same data, but just aligning the points on the x-axis, we see here that the gap in wage between men and women is quite large and actually is increasing over time, or increasing as education level goes up, right? So you see here a small gap for people without a high school degree, which grows to be quite a large gap by the time people have a college degree. All right. So essentially, the takeaway here is that by conditioning on the variables of interest, what you're trying to do is aid comparisons. And in this case, we condition by sex to reveal to allow comparisons between the male and female wages. Okay. We can also condition on other variables. So this sort of plot is what's called a small multiples plot. We call it small multiples because we have multiple plots and they're all small. Okay. And so this sort of plot actually reveals a lot of data at once and is quite easy to compare. So what we do here is we facet the plot across smaller plots. And what we can do is within each plot, we can plot several variables. So actually, when I plot the map of the US here, I have here kind of like 2 variables, right? I have latitude and longitude. And I also have some indicator of like how much this state supports or opposes school vouchers, all right? And so I have like 3 variables for each plot, but every column is its own variable of data. So we have here people who make under $20,000 to people who make over $150,000 a year on the columns. And in the rows, I have like subgroups of voters. So we have here all voters on the top row, white Catholics on the second, white evangelicals on the third. And there's actually this complete plot here, which I've linked in the slides, has like a bunch of subgroups that you can compare against. Okay, so this sort of plot is actually quite nice in terms of perception, because you can look at the change in color and kind of perceive that, for example, rich white Catholics and rich white evangelicals tend to support vouchers compared to the general public. Okay, perception. So when it comes to perceiving making a judgment call on visualizations, issues of perception come into play. And by perception, I mean the process of seeing with your eyes some visual like pixels on your screen or on a piece of paper, and then making a judgment call within your head as to what that data actually contain. Okay, and so in this sense, a lot of the principles of perception are tied closely to psychology and cognitive science, which deal with like how the human mind processes information. One outcome of these studies on perception is that the color choices that you use in your plot matter quite a bit. So for example, I have on the left the default color palette for Matplotlib for some number of years, which is called JET. And I have here the same data plotted on the new color palette from Matplotlib called Viridis. Okay, it's the same data, but if you look at these 2 plots, it looks, the conclusion that you might take away from the plots is a little different, right? So the plot on the left, we have here like this rainbow color scheme where like the dark reds really pop out at you, and then like the light blues seem really bright as well. But on the right-hand side, you see that perhaps the change in data values is not as dramatic. Okay. And essentially the takeaway here that you should remember for your own visualization work is to use a perceptually uniform color map. By perceptually uniform, I essentially mean that if the data changes value from, let's say, 0.1 to 0.2, that should result in the same change in perception to your eye as 0.8 to 0.9. Okay, so basically, like small changes in the data, like the same degree of change in the data should result in the same perception of change. Okay, so that means that, for example, here, this is not, so the jet color map is not perceptually uniform because even though like changing from orange to red is not that big of a change in the data themselves, what you perceive is like a very dramatic spike wherever you see a red square. Okay. They actually do this by running experiments on people. So they have people come into lab, and what they do is they say, okay, like please order these colors from like least to greatest. And sometimes you get a color scheme that no one can order, and that's called that's not a perceptually uniform color map. And they'll also do experiments where they say, okay, like based on these colors, like how big do you think the data are? And so people will actually record down like what they think the data values are based on the colors. And by running these like psychology experiments over and over again for a bunch of people, they can decide like which color schemes are perceptually uniform. Okay, so JET was not uniform, and actually some people at the Berkeley Institute of Data Science kind of addressed this. So a few years ago, they looked at the color maps, decided that they weren't good enough, and they proposed some changes, and those changes are now reflected in the official Matplotlib library used by people all over the world. Okay. I have the full blog post linked here on the slides in case you want to take a look. Also, as a side note, avoid red and green for a plot. So don't put red and green on the same plot because a good number of people are colorblind specifically to red and green. All right. So you can see here that I plotted what's called the perceptual delta plot for the jet color map and the Viridis color map. Sadly, the plot here is not super great, but really what's being plotted here is a straight line across the top. It's just that you can't see this line because it's at the very, very top of the plot. Okay, so this line, this weirdly shaped curve here essentially says like how big you think the change is based like from the previous value. So for example, this light blue here, when you perceive this light blue, you think that there's a big change in data values compared to what it should be. So the spike here says, I think that there's a big change even though there's not. And then here, this like kind of teal green here says it's not that big of a change, and it just kind of goes all over the place. So this color map really like kind of skews with your perception of how the data change. Whereas the Viridis color map and other perceptually uniform color maps have a flat line, which essentially means if I go between dark blue to like slightly less dark blue and light green to like slightly yellow green, that perception in data values is the same to my human eye, roughly speaking. Okay. So do keep that in mind, and Seaborn comes built in with some ways of creating some perceptually uniform color maps. But do keep that in mind, so if you see a plot out there with like some hyper-saturated colors, you'll know that they aren't following these principles. All right. You should choose a color scheme that highlights the type of data that you have. For qualitative data, we use colors that make it easy to distinguish between categories, such as choosing red or blue. For quantitative data, we'll usually use different shades of a color. Okay, so this plot on the right has both the gradients of blue and red, and also the two categories, blue and red. All right. A sequential color palette goes from like dark to bright. Okay, so we use that when we describe values that go from like low to high. Sometimes we want to display values that are extreme either on the low end or the high end, and in that case, we'll use what's called a diverging color palette. Okay, so in the diverging color palette, the middle of the palette or the zero value is very light, and the extreme negative values or the extreme positive values are dark. Okay, so for example, if I was describing the temperature in Berkeley, I could say blue is like really cold. For Berkeley people, that's probably like 55 degrees. And red is really hot. For Berkeley people, it's probably like 75 degrees with sun. Okay, so for San Diego people, it's actually worse. So I go to San Diego, and it's like when it drops below 65, everyone's like, oh my God, it's the Arctic chill. And when it goes above 75, we're like, my God, global warming is real. Okay. All right. Another interesting result of perception experiments is that not all the marks are equally good, all right? So it turns out that the human eye is a lot better at distinguishing lengths than it is some other marks that you can choose. So for example, if I have a bar chart, it's easy to see that the blue bar on the top here is slightly longer than the orange bar right below. But it's not so easy to tell, distinguish angles. Okay, so angles are not accurate. In general, you underestimate the size of the larger angle. Okay, so you'll see here that the slice for Germany is about like half the size for the Czech Republic, but it's kind of hard to tell, and this plot doesn't facilitate comparisons. In general, we frown upon pie charts. Okay, so don't use pie charts in real life. For the same reason, we don't like area charts because our judgments of area are inaccurate. For example, the box for Algeria on the very far right here, the green box, is about half the size for the box of South Africa, but it looks like the box for Algeria is only a bit smaller than the box for South Africa. Okay, so judgments of area are not accurate for humans. You should avoid those in your plots as well. Okay, for the same reason, don't use word clouds, or I suggest you shy away from word clouds. Word clouds are good as like a fun infographic, but not so good for a statistical visualization, because what people often do with word clouds is make the word itself, like change the font size of the word depending on how many times the word appears. But changing the font size of the word usually makes some words look really huge and some words look really small. Okay, and that's not an accurate judgment. It's not an accurate judgment of like word frequency. Okay, so good for fun, but not good for stats. Okay. My third subpoint within perception is to avoid a jiggling baseline. By jiggling baseline, I mean that you should try to align your bars or your lines wherever possible. Okay, so in the stacked bar chart I have here on the slide, you see that the bar's baselines change. Okay, so every bar except for the red bar in the very bottom of the stacked bar chart has a different baseline. What I mean by that is these orange bars here, kind of like the bottom of the orange bars change as the tops of the red bars change. And that makes comparisons within a color pretty difficult to make. For example, these light blue bars here look all pretty much the same size, but since the baselines are so vastly different, it's really hard to tell that they aren't changing. Whereas these red bars here are changing quite a bit, but the yellow bars are actually not changing too much at all. So it's really hard to tell if the baseline jiggles. We call this the jiggling baseline problem. We suggest you don't do this in your own charts. Instead, what you should do is facet your chart, or basically just facet your chart or use some different plot, maybe a point plot. Okay. You may also see the stacked area curve. For the same reason, you should shy away from using this sort of charts. It's really hard to read because the baseline moves. This color scheme is also like horrendous. Like my eyes are like stinging right now looking at this thing. It's pretty much impossible to tell like how countries have changed over time when the baseline changes. The only thing you can really conclude from this chart is that the overall CO2 emissions have risen over time, but you could have more easily displayed or conveyed that information by just showing a plot of the total CO2 emissions of the world over time. Instead, what we can do is just plot the lines themselves. Okay, so here in this remade plot, what I've done is I've put the y-axis on a log scale, and I've made one line for every country. I did not stack the areas on top of each other, but you can see here the overall upward trend in emissions. You can also see here that, for example, Iran has had a pretty big increase in emissions, while countries like the United States have stayed relatively the same. Actually, I think this is India. Okay. All right, let's take a break, and let's fill out attendance. So it's not going to work yet. I'm going to open the form. And go for it. Let's come back here in 4 minutes at 10:20. All right, everyone fill out attendance? Okay, turning it off. All right, doing pretty good on time today. See if we can finish a little earlier for this fine Tuesday afternoon, Tuesday morning. All right. All right, let's talk now about transformations. Okay, so when it comes to visualization, sometimes what you can do to aid your visualization is to transform your data itself before you actually plot the data. For example, I have here on the left the fares for passengers aboard the Titanic when it crashed, and it looks like most of the fares are clumped around the left-hand side of the plot, but we have a few people who have very high fares. Okay, so we call this a heavy tail distribution. And for heavy tail distributions, oftentimes what we can do to help look for patterns in the data is to take the log of the data and then replot it on the histogram. Okay, so once we've taken the log of the data and replotted it, we can see that there's a big spike at around like 2 here on the log scale. And we see another smaller spike at around 3 here, and maybe a smaller spike at around 4. All right, so by taking the log of heavy tail data, you can preserve the patterns in the data. Okay, and the reason why we can do that is because taking the log makes smaller values, kind of spreads out smaller values, and also brings in larger values. So if you take the log of a very large value, it'll be relatively small. And if you take the log of a very small value, it will be relatively large. Okay, and so it kind of is a way of dealing with these tailed distributions that's convenient for data analysis. But you do have to know how to interpret these data. Yeah, Danny? Yeah.
Isn't that also like we just talked about like perception? Doesn't that also change like the scale of how like the difference, for example, like if you look at the left graph, you know that there's a bigger spike and it kind of decreases that spike. So I know we're taking the log of it, but somebody might think that the difference is actually smaller, but it
Yeah. So Danny points out that when we take the log, we affect the perception of the plot, and that's totally accurate and true. Usually what we'll do here is use the log plot to look for like smaller spikes in the data that we might not have noticed otherwise, but we usually plot both plots. It's okay to make multiple plots of the same data with different transformations, as long as you're pretty clear about which transformation you're applying. And in this case, because we plot the original data first, we notice that it's heavily tailed or heavily clumped in one area, and then we use the log to help us notice patterns in the data. Okay, so you do have to know how to interpret these plots. Okay, so if I give you data I tell you that the data were logged before plotting them, you should be able to go back to the original data scale. And for example, here, this spike at log 2, what we can do is take e to the power of 2 and get back 7.4. For this spike at around like 3.4 or 3.2, we can do e to the power of 3.4 and get back 30. Okay, so we see here that there's maybe one spike at $7, and we have another spike at $30. These could correspond to the prices for like first-class tickets or second-class tickets or third-class tickets, for example. Okay. One note here is that I write log and exp. When I say log here, I'm talking about the natural log. That's convention for most things in this class, as well as in statistics. And when I write exp here, I'm talking e to the power of 2, which is another convention that we commonly use in statistics. Okay, so do keep that in mind. We can also log scatter plots. So we can log x and y values before applying them on a scatter plot. And by doing so, we can reveal linear patterns there that we wouldn't have seen otherwise. Okay, so in this case, what I've done here is I actually went to the World Bank, looked at the data for 2016 on countries, on how much they spend on healthcare per capita, and I plotted that on the x-axis, and I plotted the life expectancy of these countries on the y-axis. And we can see here that in general, countries that spend more on healthcare have a higher life expectancy, but the returns on spending kind of diminish over time, right? So if you're spending $0 on healthcare, you might want to spend a little bit more. But if you're spending $6,000 on healthcare per person, you might not need to spend $8,000 per person. Okay. And I think of particular note here, I'm pretty sure the US is like this point way over here. It's like we spend like by far the most on healthcare, but we have like a pretty below average life expectancy compared to other like highly developed nations. It's a sad state of the US. Okay, well that's life. What I plotted on the right is I've taken the log of the x values and the log of the y values and replotted them. And we can see here that we have a roughly linear relationship, which does have some implications for the types of models that we can fit. Okay, so when we see a roughly linear relationship, now this plot isn't the greatest for a linear regression, but it does look significantly more fitting for a linear model than the plot on the left. So if I did fit a line through the plot on the right, I can use that linear relationship on the log scale to infer some model about the left-hand scale. Okay, let me show you how that works. First, I'm only going to show you how what happens when we take the log of the y values. Okay, so what I have here is a plot of like, I believe gunpowder amounts and elasticity of like how far it moved a certain object. Okay, so I have here as the amount of gunpowder increases in an explosion, the object moves more. And if you take these, so this data is obviously not linear, but if you take the log of the y values and then replot, you get something that looks relatively linear. And so if the line fits, if there's a linear relationship when we take the log of the y values, that's equivalent to saying that the log of y is equal to ax plus b. Okay, so that's implying the log of the y values has a linear relationship with x. And we can take the exponent of both sides, e to the power of both sides, do some manipulation here, and we get back y is equal to some constant times e to the power of something times x, which is an exponential model. Okay. So if I give you a plot like so on the bottom right-hand side and show you that I've taken the log of the y values, and I tell you the slope and the intercept for this line on the log y scale, you should be able to go back and tell me these two constants here, the constant for exponent and the constant before the x. Okay, if I log both x and y, this is equivalent to fitting a model where you have log of y is equal to some constant times the log of x plus b. Okay, so this implies that the log of y and the log of x values have a linear relationship. And what I can do is, again, take e to the power of both sides, do some manipulation, and what we get out is y is equal to some constant times x to the power of some numbers. This is a polynomial, not an exponential function. So for example, if I had some data that fell on, let's say y is equal to x squared, by taking the log of both x and y values, I would uncover that linear relationship on the log scale. And then fitting that line through those values, I could uncover the polynomial degree for x. Okay, so again, I should be able to give you both log of x values and log of y values, tell you the slope and intercepts for that line, and then you should be able to uncover for me both the constant and the polynomial degree for x. And you should be able to interpret that and describe what that means. Okay, talk now about context. So when it comes to context, you saw me do a little bit of this yesterday where, for example, I labeled my plot with like this bar corresponds to a 95% confidence interval. And in general, what we want to do is take a plot that's created by default in Matplotlib or Seaborn and add some more context to it. So I have here plots. I have here the plot of, I believe this is like, I believe this is income changing over time, or perhaps number of people over time. Sorry, I was totally wrong. Let's see, percentage of bachelor's degrees conferred to women between 1970 and 2011. Okay, and so we see here that we have some lines. And the difference between the plot on the previous slide and the plot on this side is that this plot has context. So for example, I guess you just saw how it's really hard for me to interpret this plot because the year is labeled, but then the y-axis is not labeled. There's no title, so I found it hard to remember like what this plot was all about. Adding some context immediately tells me, lets me decide like, okay, what's the main takeaway from this plot? What is the plot looking at? And also, adding like these labels directly to the lines here helps me more easily see what's being plotted on this data, on this chart. Okay, so in general, if you're getting a plot ready for publication, like if you're at your company and you want to show your boss a plot, you're going to really want to include an informative title. One tip for titles is you shouldn't have, bring it back. Your title should usually be like the takeaway of a plot and not a description of the plot. So you should say something like older passengers spend more on plane tickets, as opposed to saying like this is a scatter plot of price versus age. Okay, so plots are for humans, and your title should also be for humans. Axis labels, reference lines, labels for unusual points, and captions that describe data. I believe one of our upcoming homework assignments will look at, for example, Trump tweets. Okay, and I believe that there's some interesting patterns there when you plot the sentiment of his tweets over time and label on the plot like when his inauguration date was and when his election date was. Okay, so usually adding the context to a plot can greatly inform or like really highlight what's interesting about this plot. We saw this on my first lecture where I talked about the popularity of the name Siri, right? And so when I plotted that line showing when Apple released Siri, there's like a precipitous drop in the number of babies named Siri. That's the sort of context that really adds some color and interest to a plot. Okay, let's talk about smoothing. So on the left-hand side here, I have the cherry blossom data set plotted again. This time I've used Python to plot it. And we see here that this plot suffers greatly from overplotting, which is an issue I mentioned yesterday. A lot of points overlap with each other, so it's really hard to tell what's going on with the plot on the left. On the right-hand side, I've applied what's called a kernel density estimator to the data here, which essentially smooths out this chart so you can see that there is a big peak here at like age 30 and time 5,000. And we see here that the contours show where the data can kind of show the rough trend of the data as you move to the upper right-hand side of this plot. Okay, so smoothing is a technique that we use for large data sets because when we have large data sets, we oftentimes have to deal with the issue of overplotting. You've seen an example of smoothing before. So actually, a histogram is a smoothed out version of a rug plot. So you saw yesterday that if you take every point, so let's say these are ages, if you take every point here and plot it on the x-axis as a rug plot, you see that a lot of the lines here overlap. So this is kind of like the one-dimensional version of overplotting. And when we take a histogram, what we do is we group together some of these points, and what we do is we smooth out these frequencies here so that you can see the overall trend in the data. Okay. One caveat when it comes to smoothing techniques is that they often need tuning. Okay, so basically when you smooth out your data, you have to determine how much to smooth. And in the case of a histogram, you tune that smoothing by deciding on the number of bins for the histogram. So this is a common downside to smoothing techniques that you will have to deal with in real life if you ever use a histogram or if you ever use a kernel density plot or a hex plot. All those smoothing techniques require some tuning, and that tuning is usually done by hand because there are no real good computational ways of doing it at this current time. Okay, so when you make a histogram and you really want to look at some trends, what I suggest to do is pick the defaults, but also change the number of bins and see how that changes your results. Usually you want to go for something relatively fine-grained, but not so fine-grained that you see all kinds of weird spikes in your data. Okay, let's talk now about a more sophisticated smoothing technique called kernel density estimation. You saw this yesterday when I used distplot using Seaborn. And in Seaborn, what Seaborn will do is when you plot a histogram, it will often plot a kernel density estimator on top of it, which is a smoothed out version of, which you can consider to be a smoothed out version of a histogram. And the reason why we like this kernel density estimator is because we can use this kernel density as a probability distribution for a set of data. So for example, if we have a data set and we want to simulate drawing more data from this data set, we can use this curve here as a probability density function and draw points from this distribution here. So for example, if we took this kernel density estimator as a distribution and we draw points, we would expect to see many people with ages 20 to 30 and not so many people with ages 60 to 80. Okay. So it's quite sophisticated, and I won't go into like the deep sophistication today, but I will go through the intuition behind behind how it works, and also give you an example of its use for the uniform kernel. Okay, so the intuition behind this kernel density estimator is for every data point, we'll place what we call a kernel, which is like a curve. Okay. So I have here, unfortunately it's a little hard to see, but I have here one data point at 2, one data point at 3, and one data point at x equals 5. And what I do here is I place a kernel at each point. So this here is what we call the Gaussian kernel or the normal curve kernel. And so what we'll do is we'll place a small bit of quote unquote like area or density at each point. And what we want to do is then take those densities and normalize them. So if we have 3 points, we'll divide each density by 3 so that the total area underneath all the curves is equal to 1. Okay. By doing so, we can add up the kernels, and we have here one final smooth curve that has total area equal to 1, which is why we can interpret this curve as a probability density function. Okay, so again, we take points, we add a kernel to each point, we normalize the kernels, and then we add the kernels together to get one final curve. Okay? We can change the shape of this curve by changing the kernels, right? So if we choose, for example, not a Gaussian kernel, but a kernel that looks something like a triangle, then our resulting plot will look kind of like edgy. It'll look like a mountain. It'll look kind of like a mountain range. Okay? There are many types of kernels which accomplish different purposes. For this class, you'll almost always see the Gaussian kernel because that's the default that we use for Seaborn. Okay, so actually when you make a dist plot in Seaborn and it plots the kernel density estimator or the KDE, what it does is that following procedure underneath the hood. It places a small Gaussian at every single point in your data, normalizes all of them together, and then adds them all up. So you can see here like a small hump here and a big hump here. Okay. You can also change a kernel by changing how wide it is, and we call that changing the bandwidth of a kernel. So for example, you saw in my previous slide that I can put a small Gaussian at every single point. If I make those Gaussians really narrow, which is totally valid to do, then I get a spiky kernel density estimator plot at the very end. But this is analogous to making the bins of a histogram very narrow. Okay, so the result is I smooth less so that I get more fine-grained detail in my plots. The drawback is that if I make my bandwidth too narrow, as with the case in the histogram, the plot will contain some noise and it'll be a little bit hard to interpret what's going on. Okay, so let me give you an example using the uniform kernel. Okay, so this is something that you should be able to do. If I say like, take a plot, I'm going to use a uniform kernel with some bandwidth, and you should find me the height of the curve at some points. Okay, so if I have the data points 1, 2, 5, and 8, then what I can do is plot the uniform kernel at each x. The uniform kernel is just a flat line. Okay, so it's not like this weird curvy thing like the Gaussian. It's just a flat line. And so unfortunately on this plot here, we have, oh my gosh, this is so obnoxious. Hello. Okay, we have here the points 1 and 2, but those points are a little bit hard to see because the kernel kind of overlaps with them. But you can see here that we have one kind of box at the x equals 1 and one box at x equals 2, and those two boxes overlap with each other. We have another box at x equals 5 and another box at x equals 8. The bandwidth 2 for this particular example means that the width of that uniform distribution goes from 4 to 6 for x equals 5. If I had the bandwidth of 1, then the width of that box would go from 4.5 to 5.5 when I have x equals 5. Okay, so the width of those distributions, or the width of those kernels, are narrower if I narrowed the bandwidth. Okay, I have 4 points, so I'm going to scale each kernel by 1/4. And then I'm going to add up the kernels together so that I get the following smoothed out plots. Okay, so I have here kind of like one little step guy at for these 2 points here, and a smaller little bump for x equals 5 and x equals 8. Okay, and I can see here that because I've added between 1 and 2 kernels together, the height of this curve here at x equals 1.5 is 0.5. So it's higher than the rest because there's more density there. Okay, any questions about this? Okay, well, it looks like I'm going to get my wish and finish a little early today. In summary, consider those 6 principles when you make a visualization. If you actually go on Google, and I've done this myself several times, and you Google search up on Google Images like good data visualization, I can like guarantee you that 95% of like those plots there like fail to adhere to almost all these principles. So I suggest to you, if you want a fun exercise, and you might do this also in discussion, to go online, go do that Google search, and just practice like applying those principles and see if you can spot or fix some of those plots there. And it'll help you do better data analysis and better data visualization. In general, our philosophy for visualization is to show the data. Okay, so we cut out all the cruft. Edward Tufte, one of the world's visualization experts, has this idea called the data-ink ratio, where basically every mark that you make on an image or a piece of paper should be related to the data if possible. So you should minimize the amount of black ink, as he says, that's not directly tied to a data point. And by doing so, your plots will hopefully show the data and be more clear. All right, I'll see you tomorrow.